Okay, for this problem, you're asked to find the second derivative of y with respect to x for this relation right here. Here's a graph of that relation. It's not a function, doesn't pass the vertical line test. And I'll just draw your attention to the fact that you actually could do this problem using explicit differentiation. You could solve this relation for y in terms of x by realizing that this is quadratic in y. So in effect, if you write it this way, a equals 1, b equals minus x, or the opposite of x, and c equals x. And so by the quadratic formula, y equals the opposite of b, which is x, plus or minus the square root of b squared, minus 4 times a times c, where c is x, all over 2. And you can see here that I've, on Desmos, graphed all three of these, and they overlap each other. This f sub 1 of x is the top half of each of these curves, where we've got the red dots, and f sub 2, where we have a minus sign, is the bottom half. Okay, and now you could find f prime, f sub 1 prime of x, and once you've got that rule, you could find f sub 1 double prime of x. And similar here, okay? But we're doing it implicitly. So we'll use the product rule on the left, first times the derivative of the second, plus the second times the derivative of the first. And then on the right side, the derivative of x is 1. For y squared is 2y, y prime. Let's get y prime by itself. So we'll move this term to the left and the y to the right. Factor out the y prime and divide by the coefficient of y prime. There's the definition of y prime. Now to get y double prime, got to use the quotient rule. So here's the denominator times the derivative of the numerator, minus the numerator times the derivative of the denominator, all with respect to x, over the denominator squared. And if we distribute these and combine similar terms, do some stuff, the whole idea was to get this y prime kind of sitting out here by itself. So hopefully you can see how to get from here to here. And now, what is y prime? Well, we found it here, so we're going to substitute that expression for y prime into this definition for the second derivative and simplify. We have a complex fraction because we got this little fraction in the first term of the numerator. And we're going to multiply numerator and denominator of the big fraction by this denominator right here. Okay, and that'll turn this into a simple fraction. So when I take x minus 2y times this first term, the x minus 2y's cancel out, and I get 1 minus y, this factor, times 2 minus x. Take x minus 2y times this term, y minus 1 times x minus 2y. And when I take x minus 2y times this denominator, it just raises the exponent by 1. Okay, now you could use FOIL to multiply these two binomials, FOIL to multiply these two binomials, check to see if there's any similar terms or if anything cancels out. I think you actually do get some terms that cancel out, minus 2y and a plus 2y. I think you end up with it that combined is 0. But I'll let you take care of that. And for sure, the denominator is x minus 2y, the quantity cubed. So if you want to find the concavity of these curves at a given point, you need to know the x and the y coordinate when you're using this formula for the second derivative. If you do it explicitly, you can find the concavity just by substituting x. Okay, There you go. Hope that helped. If you have any questions, post a comment.